Hello and welcome. In this presentation, I'll discuss how to develop a future state value stream map. We currently have a current state map for a company. The customer is State Street Assembly, who has a demand of 18,400 pieces of steel brackets per month. These steel brackets come in two forms, left-hand drive and right-hand drive. So we have to, as a company, make 12,000 of these left-hand drive and 6,400 of the right-hand drive. These products are sent in trays, each tray containing 20 pieces, and these trays are then put in a pallet and then shipped to the customer. The customer operates in two shifts, and these shipments from our company goes every day, daily shipments. The customer provides us 90-day, 60-day, and 30-day forecasts electronically, and then also provides daily orders. These daily orders then become this information that we have for the forecast as well as daily order is what comes to the production control department of the company that we are focusing on. And the MRP that they use is then determining what the weekly schedules will be for different departments that they have or different processes that they have. They have a stamping process, they have a spot weld 1, spot weld 2, assembly 1, assembly 2, and shipping. So as we can see, these weekly schedules are sent to each of the processes based on the MRP run. The production control department also sends 6-week forecasts as well as weekly forecasts in the form of a fax. So 6-week forecast electronically and weekly forecast uh, by fax to the supplier, which is Michigan Steel Company. And then the company sends steel coils, 50 feet steel coils on Tuesdays and Thursdays to the company that we are focusing on. And therefore we carry 5 days of coils as inventories so that we can continue with our processes. At the bottom of each of the process, we see the data sheet for each process. So we have cycle times, we have changeover times, we have the reliability of the process, we have how much time it spends working on something in every shift. And for specifically stamping, we have every part in how many weeks do we make. So because this is a very fast process, its cycle time is only 1 second, we have every part which is made after every 2 weeks. Right? This 27,600 is because this company operates for 8 hours. So there's 8 hours times 60, these many seconds in a shift. But then there are two 10-minute breaks in which nothing is produced. So minus 2 times 10 times 60, which will give us 27,600 seconds. So that's the time available every shift to make something. So that's the time that we see there. And similarly, we can see for every process, we have information about their cycle time, their changeover time, uptime or reliability, how many shifts it works, and each shift, how many seconds do we have available. We also have information about the inventories, work in process inventories in between different processes. So right-hand drive and left-hand drive, we have information about that. And all that needs to be accounted for while we are looking at how much value addition can be added. All that information about inventories, changeover time, cycle time is then translated into the value added time, or rather the total lead time, production lead time, which is what we have at the bottom, 5 days of inventories, which is the coil inventory, and 1 second, which is for the stamping process. This inventory can then be converted into corresponding number of days, which is 7.6 days in this case, 39 seconds for spot weld, and so on and so forth. So we have production lead time, which is 4.5 days. 23.6 days. 4.5 days is just this inventory time. So 23.6 days. And then processing time, which is 188 seconds. So using this information now, we have to understand what could be the future state map. First, understand what the problem here is, and then determine what could be a suitable future state for this company. So first thing we have to ask is what's wrong with this company, Acme, the name of the company, its value stream. So what we observe is that there is mass production. There are large lots being produced. Then they are pushed forward because the MRP is being sent weekly to every process independently. So they have their own forecast, which they are building every week. So there is an island mentality for every process, and hence these lots are being pushed forward by each of this process. So what happens is that we have 3 value-added processes, which are stamping, spot welding, and assembly. And then there's a traditional mass production going on because the focus is on economies of scale. And these batches are resulting in a lot of waste, a lot of inventory sitting in between processes. And overall, if you look at the value added time versus the time in plant, so this is 23.6 days. That is the time in, and that we saw up here was 188 seconds, about 3 minutes. So we see there's a big disparity between the value added time versus the total time it takes. And our objective should be to remove this non-value added time as a proportion of the overall time that is being spent in the plant. Here, the focus is mainly on make more faster. That would be best strategy for the company. Now, whether this is good or not is something which we can see from a lean systems point of view. Clearly, wastes are something to be avoided and removed, and clearly from that point of view, this is not good. So the question is, what is it that we will be eliminating from this current state? Now, in the case of value stream mapping, one of the first thing we are focusing on is overproduction. That's the elimination which we are trying to achieve here. And if the material is not needed, but then has to be handled, counted, and stored, that would be considered a waste. In addition, you also have problems of defects. It also results in many of the processes working on things that are not necessary at this point in time, and all those things are considered to be waste within lean systems. So overall, we have different types of waste: overproduction, waiting, transportation, unnecessary processing, inventories, unnecessary motion of people, and then having to correct problems. So those are the different kinds of waste that will waste a person's time or talent, and we want to ensure that such kinds of waste can be eliminated from the system. So value stream helps in attacking overproduction, and in turn, many other problems are also solved by means of this. So the objective should be not just individual processes being very efficient, but the overall system being efficient. That's the objective of our value stream map, future value stream that we are trying to develop. So the question first is, what is flow? Like what should be the speed at which we should be producing? If it should not be mass production, then what should be that speed at which everything should be operating? So this question needs to be viewed from the point of view of the problem that push processing or batch-based production creates. So as we can see on the top here, this is our batch and push processing. And here we can see that each process is independently making products. They have their own times. And based on this time, everybody is making those many products for the next in line. And hence, the lead times are greater than 30 minutes for the total order because everybody has to spend enough time to make that batch. When we convert that into a continuous flow, what happens is we are making one and moving one. So that's what is going on at the bottom. So we are now putting all these three different processes together. So when one of the product has been made, or whatever the process had to do at step one or step A, it goes to the next one in line, and then that next step does its task, which is B, and then the third one. So everything is being done one at a time. So that would be a continuous flow. And the question always comes whether this level of continuous flow can be achieved in an operation or not. Many times it might not be possible. So we have to understand which are those places where we could achieve it and where we have to do something else. Now, having that understanding, we have to now understand at what speed should these uh, products be made? What is the rate of production that is needed? And in organizations, one of the very important thing to keep in mind is that when we are trying to make an organization efficient and effective, the objective should be to match the rate of production with the rate of sales. So we have this concept of takt time, where takt is a German word that means beat or pace. And that determines at what speed the entire production should be making products. So here, takt time can be calculated by looking at what the effective working time per day is and dividing it by the customer requirement per day. We know that the effective working time per day is the total time that we have in a shift, 28,800, minus the time that there's a break, 10 minutes break. So that's the 27,600 in the numerator. And the denominator, we have customer requirement per day, which is 460 pieces. Actually, this is per shift because this can be translated into per shift also, or we could consider it as per day. So this is per shift information that we have in the numerator. So if I have to take it as per day, I would have to multiply this by 2. And customer requirements per day is something which we are aware of. We have 18,400 products that we have to make for the customer, and we know that in the particular case we are operating for 20 days. So total number of products that have to be made on a monthly basis are 920 of them, which means that these are the products to be made, sorry, on a per day basis, 920 units per day, so that we can make 18,400 pieces per month. That 920 per shift can be considered as 460, which is what we had done earlier. Or if you want to use it per day, which is what you see in the formula, I could multiply this by 2, which is 920 in the denominator. So instead of multiplying with 2 on both numerator and denominator, we have just taken it effective working time per shift divided by customer requirement per shift. So that gives us 27,600 seconds divided by 460 pieces, which is equal to 60 seconds. So the pace at which we should be producing is 60 seconds. So that's something which will dictate quite a few things as we go forward. Now, continuous flow is not necessarily possible everywhere, specifically when we have processes which have long setups, or if there are large distances between two processes. For example, if a supplier is located quite far from our organization, it's not possible to have a continuous flow between the two organizations. Or if there are downtime problems, or if there are long lead times involved in a certain process, then we cannot really use continuous flow, and we have to find alternative mechanisms that still can preserve the positive aspects, but find some way in which we can handle these specific issues that don't allow continuous flow to work well. And some of these approaches that we can use are, for example, Kanban, by creating a signaling system between upstream and downstream processes that helps with some bit of movement that can be coordinated, even though it not be completely continuous flow. Or using two bin kind of approach, where again, this is a signaling system where these bins act as a way to regulate the production between upstream and downstream processes. Having some buffer stock sometimes is necessary. Therefore, continuous flow may not be completely possible. Hence, we keep some buffer stock. And then supermarket is a concept which can also help in controlling the quantity of inventory. It also provides a visual control and something which is owned by the supplier. We will look at supermarket a little bit more detail in coming slides. So here is an example of a supermarket pull system. Essentially, the objective is to control production at the supplying process. So we have a supplying process here, and we want to control the production at this process without trying to schedule that process. Essentially, this should produce based on what the demand at the customer process is, right? So what we do here is that we have Kanbans, withdrawal Kanbans and production Kanbans. And there is this supermarket that we have established where products will sit in or cards will sit in. The withdrawal Kanbans are the ones which trigger the movement of parts. Right? So these are the Kanbans that reside at the process cell, at the customer process cell, and is given to the supermarket. So it comes to the supermarket. And at that time, the customer process takes a product and takes it to process step B and then start working on it. So that's a movement of Kanban that triggers information or gives information to the supplying process that a product has been withdrawn from the supermarket. It's something similar to the supermarket that we see in real world. Like when we go to a retail supermarket, we see these shelves in which products are. So anytime a product is taken off the shelf, there has to be some way that the uh, inventory, the warehouse where the products are kept, can then be brought back to the shelf so that it's replenished as seamlessly as possible. Similar concept is being used here. The only difference is that we're using visual signals in the form of Kanban here. So withdrawal Kanbans are ones owned by the customer processes, and it comes to the supermarket as and when a product is withdrawn from the supermarket. And once that happens, when the withdrawal Kanban has been placed back in supermarket, the production has to begin for supplying process so that there is a replenishment activity. So this production Kanban, it resides in the supermarket. It's something which sits in the supermarket. So once that withdrawal Kanban comes here, the production Kanban is taken from the supermarket by the supplying process, and then they start working on producing this product, which might be needed again. So then that product is brought back to the supermarket and it's kept in that supermarket to be used by the customer process later on. So this is the way a supermarket pull system works, and it helps in coordinating the upstream and downstream processes. Now, the pull system between processes help us get an accurate build instructions between the two processes, specifically to the upstream process. The supplying process knows how much to build without trying to predict downstream's demand. So there's no forecasting going on for the upstream process. The pull by the downstream process then determines what the upstream produced, when did they produce, and in what quantity did they produce. So the downstream process, that is the customer process, also knows what exactly upstream is doing. The supermarkets typically are located near the supplying process, so they own that in terms of what exactly is going on in the supermarket. And then they're only used when continuous flow is not possible because of all these reasons that we mentioned earlier. And there's a cost involved with supermarkets also, which is in the form of some inventory that we're carrying there and some material handling that is necessary to move products between two processes through a supermarket. So there are some costs, but overall, the net benefits outweigh the costs involved here. Now, in value stream mapping, also the other thing which we have to keep in mind is that we don't want to schedule every single process like we saw in the current state map. We want to schedule only one point. Now, if pull systems schedule upstream processes, we can schedule that one point in the value stream, which we call the pacemaker process. And the idea is that there will be no supermarkets after that scheduling point or after the pacemaker. So only supermarkets that we will see in a value stream will be upstream from that pacemaker process, wherever that pacemaker process has been established. So we will take a look at that as we go forward. Now, the question we have to ask for our current state map is, where can we use continuous flow processing? Now, let's look at the situation that we have at hand. We have, let's say, a welding station with 39 seconds. We have welding 1, 39 seconds, welding 2, 46 seconds, assembly 1, 62, and assembly 2, 40 seconds. So we have 4 processes. Let's just take that in consideration here. So let's say we have this welding 1, so W1, welding 2, we have assembly 1, A1, and A2 is assembly 2. Each of them have a specific time, and we already have established what our takt time is supposed to be. The pace at which we should be making is 60 seconds. So let's put that 60 seconds as our upper limit here, sort of upper limit. The welding station 1 makes it in 39 seconds. So 39 seconds would be approximately here. So this is the time it takes at welding station 1. Then we have welding station number 2. So let me just make this again here. Welding station number 2 takes 46 seconds. So maybe perhaps somewhere here. So this is the time it takes. So this is 46 seconds. This is 39 seconds. And then we have assembly 1, which takes 62 seconds. So it takes a little longer than the established takt time. So I'll just put that here as 62 seconds. And then we have assembly 2, which takes about 40 seconds. So just a little less than welding number 2. So we just put it somewhere here. This is our 40 seconds. Approximately, that's what we have in terms of our processes and the time it takes for every process. So in total, these 4 processes are taking 187 seconds, right? And we know that we are currently going beyond the takt time, so we have to fix this situation overall. Now, we want to understand approximately how many people do we need actually to establish the 60-second takt time if our total time right now is about 187 seconds. right? So total welding time is 187 seconds and takt time is 60 seconds. So if we divide the 187 total time with the takt time, which is 60, this should tell us approximately how many workers might be necessary to actually establish a process setting, which can enable us to achieve that takt time of 60 seconds. So this gives us 3.12. Now this is just a little bit more than three, um, but four. Right now we have four people for each of these different processes. We have one person involved, so four people being involved is a bit too much compared to what we are needing here. 3.12 versus 4. So the question is, what can be done here? The thing that happens in such situations is that these are the instances when we engage in process kaizen, which is we try to understand if we can do something about these four processes, either combine them, create a cell with these kinds of processes so that we can get this thing done with three people. So that would be a great thing to achieve because it's very close to the number that we actually are striving for. And also, if possible, try to reduce the time that it takes for every workstation that would have been created by this cell that we have developed, or combining few of these activities that we were earlier doing separately, such that the time that it takes in each of these processes are just a little less than the takt time, so that we are not right on that takt time and we have some buffer, um, just to ensure that we are able to create the products without having to worry about being sometimes above the takt time. So that's the objective that we will be achieving through some Kaizen events, process Kaizen events. So what we could do is something like going from this situation that we had to a situation where we could, for example, create a welding station followed by a combination of welding and assembly to a certain extent, let's say. So this is welding station, welding and assembly, welding continues. Somebody could be doing welding and assembly, and then there is an assembly. So let's say we could do something like this, and each of them is handled by one person. So now we have three people, and we can reduce the time there. So if this is our takt time of 60 seconds, we could make sure that our cycle time for each of these individual processes that we have restructured or redesigned is just a tad bit less than our takt time of 60 seconds, right? So that's the objective, maybe 56, 55 seconds, whatever that might be. So this is how we would like to redesign our processes so that we can achieve what we are striving for here. So here is an example of what could happen. So this is what we have done. This was the welding and assembly separately earlier. Now we have one single cellular structure where we have three different workers involved, and each of them is basically working on welding assembly, and then finally assembly. So all three of them are involved here. The takt time was 60 seconds. We have calculated that cycle time. We want to make it a little less than the takt time. So in this case, let's say we have it at 56 seconds. We want to make sure that the changeover is zero. And then we want also reliability of 100%. This is two shifts. So these are the kinds of things we are doing through process Kaizen, right? So this is what we achieved through a process Kaizen. Kaizen stands for improvement in a given process through focused approach, a team-based approach, where these events are then focusing on improving the process output at a given point in time. So we have the stamping process like we had. Now we have this combined welding and assembly. And then between welding and assembly and shipping, we have put a supermarket. So that's the supermarket with left-hand drive brackets and right-hand drive brackets having its place where we will be keeping them. Between this supermarket and the welding and assembly, we have the flow of Kanbans. So this is how we will be regulating how welding and assembly should be making anything. So that Kanban will dictate at what pace this particular process should be operating. From the shipping and staging process, we then send the products to the customer daily through a truck shipment. Okay, so that's something which we were doing, and that's how we will be continuing the process so far in the first view. This is our first view with regards to the future state. Some changes we can see already in terms of a process redesign. Now, the next thing is to think about stamping and raw material supermarket. So, what do we do with the stamping process, and what do we do with the way we get the raw materials from the supplier? Now, stamping process is a very fast process. As you can see, the cycle time of that process is 1 second. So it actually produces or stamps these metal parts very quickly. So within 60 seconds, which is what our takt time is, it would have already made 60 parts. So the question that we have to, and then the changeover is quite long. So we have to think about this as a special kind of equipment that we have, which is being used by several different products within the company. And it needs some trigger point of how much to make in this particular process so that we can maintain low levels of inventories, yet be able to ensure that the stamping process is operating at the best possible way it can. So the way we typically do it is that when we have some special equipments like this, then we create something called a signal Kanban for that particular process or that equipment. And we would maintain some bit of inventories because this process, once we start running, we have to ensure that it is operating enough, it is making enough parts. But instead of the situation that we had in the current state map where every part was made every 2 weeks, what we want to achieve is much lower than that. So every few days we want to come back to making something on this particular equipment. And obviously, to be able to do that, we have to also work on the changeover time or setup time and reduce that setup time. So these things have to happen simultaneously, reducing the changeover time and at the same time thinking about keeping some inventories, but way lesser than what we used to keep. So in this case, what we would do is we will create this signal Kanban, which is sent to the stamping process from the supermarket that we would have between the stamping process and the next, which is our welding and assembly combined. And then stamping is supposed to make these parts or stamp the parts as these cards come to them, signal Kanbans come to them. Uh, and this signaling is happening when there's a trigger, a minimum level that we need to maintain. So we for example can be establishing something like a 1.5 days worth of inventory that we want to keep, way lower than 2 weeks, and that's definitely an improvement in terms of the inventory that we will be holding. So the signal Kanban typically is shown as an inverted triangle that we see here. Now, for raw materials, we are relying on supplier. So obviously, the Kanban concept is not that straightforward because we cannot just send that Kanban on an instantaneous basis to the supplier. Now, to be able to do that, we could set up a third supermarket. So we already have two supermarkets. One is between the welding and assembly station and the shipping station. The other one is between welding and assembly station and stamping. And now this would be the third one, which we will be establishing between the stamping and the supplier. And the way it's going to work is that the uh, the company Acme, they can attach an internal withdrawal Kanban to every coil that they receive from the supplier, and then these Kanbans are sent to its own production control department because that's the one which coordinates the information. Whenever another coil is needed, that control department, production control department receives this Kanban, and then production control can order the coils based on their actual usage by the stamping press. So they know that stamping press has just withdrawn something, and that then goes to the production control department as a production Kanban, which is an information that can be transmitted to the supplier, informing them that we now need the next shipment to come to us. So that way, the production control department becomes the place at which these cards will be coming as production cards and or production Kanbans, and that will then be transferred to the supplier as information. And there should be some discussion about being able to have milk runs for daily deliveries rather than delivering twice a week, which is currently the situation. If there is a possibility of doing daily deliveries, then that should be explored within the system. So that's something which we could do as part of, again, some discussions with the supplier and understanding what can be done for the raw material that we're getting and reducing the inventories that might be carried at this point in time. So this would be our second view of the future state, where we have a supermarket in between the welding and assembly and shipping. We have a supermarket between the welding and assembly and stamping. And then this is our signaling Kanban, which is for informing the stamping press how much to make. And then we have the third supermarket, which is between stamping and the raw material supplier. So this is what we have achieved so far. And this information that we see here, this transfer of Kanbans, production Kanbans to production control department is how we are understanding how much stamping has made and how much needs to be obtained from the supplier in terms of the steel coils. So that's the information. Then they transfer that information to the supplier. So that's how it's operating right now. Now, what we're going to see is at what pace we should be, or rather, where should we schedule within the system, because we want to have one point that should be scheduled. Not everything should be scheduled. There should be only one process that needs to be scheduled. And what should be that schedule like? What is the way we will be making the product? So to be able to understand this, we have to understand the concept of pacemaker process. How do we level the production mix that we have? We have two different products that we're making, left-hand drive and right-hand drive brackets. So essentially a mix of product. And the idea of pitch, which is at what frequency should we be making these products. Okay. Now, pacemaker process is that process which we will be scheduling. It's just one process that we'll be scheduling, and that will dictate how everything else should operate. And this will be the newly designed welding and assembly process, because that's one process which has quite a bit going on there. There are three different workers involved and different kinds of activities that has to be done. And it's the slowest process right now between everything that we do. So that would be our pacemaker process. Leveling the production mix. Now we have a requirement of 18,400 pieces per month divided between left-hand drive and right-hand drive. We have an option. We have to make 920 pieces every day. We know that also. So we have an option to make these 920 pieces, which is divided between left-hand drive and right-hand drive, in such a way that we make all the, let's say, left-hand drive first, followed by the right-hand drive, or vice versa. That would be one way to do it. But that would be an example of a batch processing, which we are trying to avoid here. So here is the idea of leveling the production mix, which comes into play, and it helps us avoid that batching here. So the way we are going to do this is we look at the daily requirements of 12,000 left-hand drive and 6,400 right-hand drive. And we know that the left-hand drives are approximately twice that of right-hand drive. So we could have this one approach, which is we make one right-hand drive followed by two left-hand drive. Then we make again the right-hand drive steel bracket followed by two left-hand drive steel bracket, and so on and so forth for both shifts in a day. And this would eventually make us achieve the same objective that we would have achieved had we produced all the left-hand drive first, followed by right-hand drive, or vice versa. But the advantage of this is that we are now ensuring that we are producing in concert with the ratio at which the consumption is actually happening, because we always want to have the rate of production to be similar to the rate of demand. Now, this is only achievable if we have reduced the changeover times between these different products that we're making. So that's a very important aspect of going to such kinds of production mix, leveled production mix, that we need to also work on changeover times and reduce them. So this would be an example of the way this particular company can think about leveling their production mix. And then the question is, at what pace or at what frequency should they be making it? So when should we know that, okay, this is time for the company to make the left-hand drive now, or the second left-hand piece to now, or the next right-hand piece now? So we need to give some instruction to the pacemaker process in the form of a pitch, which is telling that process what is the increment of work, when should we make the next thing, and how many should we make. And the way we calculate that pitch, which is basically the consistent increment of work, is taking the takt time and multiplying it with the pack size. So we know the takt time, which is 60 seconds, and we know that we are keeping these in these trays, which is our pack size, and each tray contains 20 units. So when we multiply 60 seconds with 20, we get the pitch, which is 1200 seconds, which is essentially 20 minutes. So that 20 minutes then becomes our pitch, which is after every 20 minutes, the pacemaker is given instructions to produce one pack quantity of a certain part that is being made. and then also at the same time take away one finished pitch quantity to the shipping. And that's how the idea of pitch comes into play, that it helps in coordinating in a certain frequency different processes that are involved. So this is what will happen, that this is the way we show a load leveling box, which essentially does what we just talked about. The material handler pulls the kanbans out of the leveling box one by one. So this is O, and X basically refers to production of different types of products that we're making. So they will be picking up in the frequency of 20 minutes, in kind of spread of 20 minutes for each of these different products that we're making, and then moves the tray of brackets from the finished goods supermarket, that is this one, to the staging area, which is here. And from the staging area, we are actually trying to fill in the truck, which then will be shipped on a daily basis, one by one, according to a withdrawal Kanban. So that's something we discussed earlier. So essentially, this daily orders are being sent at a frequency of 20 minutes. And then that is how, and the products are to be made one after the other. So right hand followed by left hand, a sequence that we have decided based on the ratio at which our customer wants this product. So now this is our overall view now based on all that we have done. So we started with an understanding of how this current stream map is. We worked on the idea of creating a cellular structure here between for welding and assembly, so that we can ensure that we can get these things done with less number of resources. And also we reduce the changeover time here so that we can actually achieve multiple products or different types of products within that cell. We also thought about different supermarkets. So one, second one, and the third one, these are the supermarkets that we have to have so that we can coordinate multiple processes here. We thought about the speed at which everything is working was obviously the first thing we had to think about, which was the takt time. So we did this also. And we also decided what should be the pitch for our company. In this particular case, it's 20 minutes for this company's situation. We know that it's going to be 20 minutes. With all those changes, what we observe is that we obviously have reduced the processing time a little bit, but what we have reduced quite a bit is the non-value time in terms of the inventories that used to be there due to overproduction. So this now has come down from 23.6 days to 5 days. And the processing time has also come down a little bit to 166 seconds. So this would be a dramatic improvement to what we used to have, and something which helps the organization um, increase the value added steps within the company as a ratio of the total time it takes for producing products. So this would be one example of the way in which the organization can go from current state to future state. Now, a way to think about this could be to think of it in terms of different loops that we had worked on. So we could think of this particular loop as a pacemaker loop, where we have the welding and assembly station providing products to the supermarket, from where the finished goods are being sent to staging. So there's one loop that we worked on through things like reducing the work content. We also did the uptime improvement. We reduced the changeover time. All these things were happening in the pacemaker loop. We also worked on the stamping loop, because the stamping press is a sort of equipment which is a large equipment which is used by multiple products. So it had to be handled in a specific way using signal Kanban. So we use that. Some batch processing is going on here. So that was a special thing we had to do for stamping loop. Then we had the supplier loop, where we had to understand how we can coordinate between the supplier and us all the raw materials that are coming in using the Kanban idea and the supermarket idea. So we used the production control department and took advantage of the information flow that production control department is already having with the supplier. So that would be our supplier loop. So overall, these loops then help us understand how we can manage different kinds of loops and manage the overall value stream, which can deliver much higher value addition than what otherwise the case was. So in this presentation, I discussed a way to create a future state map from a current state map. Some of the concepts that are important, like takt time and the idea of signal Kanban, the idea of supermarkets, the idea of pitch, pacemaker, etc. And we understand how all of them come together to improve the system level efficiency rather than focusing on just one process. So this then helps an organization add value in different things that they're doing. Thank you.